Welcome to the MuAnalysis video on recognizing solderability failures. MuAnalysis is a failure analysis laboratory. This video will discuss bad solder joints in PCBs, specifically where we find insufficient solder, mechanical damage, coefficient of thermal expansion mismatch, and blackpad. This is an X-ray of a power LED. The circle is a heat spreader pad. Poor solder coverage inside that circle can lead to overheating. On the left, the part has a bad solder. This is a reference part that has not yet failed. On the right, the part was heated to the point that the solder melted and re-solidified. This was caused because insufficient solder was applied. This is an X-ray showing pin connectors soldered to vias. The red arrow shows a via that has not been filled with solder. This violates the IPC A610 standard. Flexing the board can cause solder cracks in opposite sides of a BGA ball. Here we have a capacitor that has been stressed either mechanically or by temperature excursions. Instances of voiding can be seen in the solder. The solder has cracked following the grain boundaries. The part has passed the stress test and has not yet failed. However, it shows vulnerability and is subject to early failure in the field. On the left, the ball crack is hidden from view because the solder is wrapped around the pad. On the right, the crack is also hidden, this time by the solder mask. These two examples cannot be seen by a visual inspection. A two-dimensional X-ray will not see these, and even a three-dimensional X-ray could miss these as well. Localization is best achieved using cross-section. Let's look at coefficient of thermal expansion fatigue. We see a cross-section of a surface-mounted IC pin soldered to a board. The two top images are optical images and the bottom is a scanning electron microscope image of the optical image on the left. The pins are not copper and are soldered to copper solder pads. The differential thermal expansion of the pins compared to the pads have stressed the solder. The components of the solder have separated into different domains, which means that some are brittle and subject to cracking. Blackpad is a surface corrosion of the nickel layer of solder pads in printed circuit boards. It occurs during gold plating in electroless nickel immersion gold, or ENIG. The corrosion makes the gold look darker, hence the name blackpad. The corrosion results in poor wetting and a weak solder joint. The surface corrosion is not uniform across the board. This is an X-ray of a ball grid array, or BGA, on a board. A telltale sign of blackpad is the presence of champagne bubbles in the solder, as shown by the red arrow. These are SEM images of a ball from the previous slide. A dye was injected under the BGA, then the BGA was pried loose. We can see why this is called champagne bubbles due to the porous nature. The images on the left are high magnification SEM images of solder pads showing mud cracks. On the right, we see cross sections of the images on the left. The top right image is a high magnification SEM image, and the bottom right is the maximum magnification optical image. On the top left image, we see cracks at the interface between the solder and the nickel, and the absence of an intermetallic region. The bottom are optical images of the images above. In a good region, the intermetallic forms well. In the corroded region, the nickel gets consumed and the intermetallic has problems forming. The hairy intermetallic is a characteristic signature of blackpad. This is a SEM image of the mud cracks remaining on the solder pad after die and pry. The image on the left side shows a tantalum capacitor that has fallen from the board, and the middle image shows that the solder has adhered to the capacitor, but not the board. On the right, an X-ray image shows that the solder never wetted the pad. On the left image, an energy dispersive spectrum shows the accumulation of phosphorus in the corroded nickel. To summarize, we have seen several examples of solder joint failures and looked at the methods to determine the root causes. Thanks for watching.